To be here. So you will notice that my description of myself does not anywhere include the word coding, programming, anything like that. I don't code, and I'm here to talk to you about a coding topic. So I'm going to be a little more dependent on my speaker notes than usual because I really want to get this right because it's fascinating to me. You can sort of think about this as somewhere between a book report and a love letter. It's a bunch of conference talks and papers that other people did over probably a 3 to 5 year period. And I stumbled across it and just got hooked. It's completely outside of my swim lane. So I'm really here to tell you about it and hopefully share that enthusiasm and get you hooked on it too. In 2012, I went to a conference called ShmooCon in DC. Who here's been to ShmooCon? Yay, it's excellent. And when I go to ShmooCon, I make a point to try to go to talks that are not only talks that are relevant to me, but talks that look like something I know nothing about. I've seen some of my favorite talks that way. The mainframe hacking talk this year, I mean, that, again, I don't think I've ever actually seen a mainframe, and that's one of the best talks I've ever seen. In 2012, by far the best talk I saw was this talk on the science of insecurity. Sergey Bratis and Meredith Patterson and their co-collaborator, Len Sassaman, was unfortunately not able to participate. So the thing that they said that really struck me is that insecurity is really about computation. So our trust in a computing system is really based on what that system, we think that system can and can't compute. If you make an assertion of trust, you're asserting that it will do what you expect it to do. Will it expose your data? Will it be vulnerable to somebody getting a shell on it? And the way that that takes form is each system receives input and it has to decide whether that input is good or bad. Does it accept the input and act on it, or does it reject the input? Can you trust it to make that distinction and to only act on valid input? When you start to think about it in this way, what they said was that exploitation is unexpected computation. So an exploit is, at its core, something that you run on a target and it causes the target to do something you didn't expect. It is a program captured in input, and there may be computational structures on the target that you created without intending or without even knowing they were there. So I had been working in tech for over 15 years at that point and in information security for over a decade. And that talk fundamentally changed my perception of cybersecurity. I wanted to learn more about this. And they mentioned in that talk, another talk the previous year on dwarf, which, what the hell is that? Okay, let's go find out. Unfortunately, ShmooCon, God bless them, puts all their talks online. The ShmooCon archive on archive.org is just one of the best things on the internet. And so there's this talk about how dwarf is Turing complete. I was a medieval studies major in college, and I'm a huge Tolkien nerd. So the fact that they were so committed, they translated their title slide into Dwarven runes, I am all about this. I got completely sidetracked trying to see if I could still read it, because at some point I could read Tolkien Dwarvish in line. Can't anymore. Untranslated, they were talking about exploiting the hardworking dwarf. Again, bear in mind, I don't know what dwarf is. Their first slide was an executive summary. I'm doing pretty well, I'm hanging in there. And then they start talking about bytecode and stacks and return to libc attacks. I may have been working in tech for 15 years, but I don't understand any of that shit, right? So I could have asked Mike, my partner codes, and he has answered my dumb questions for, over 2 decades now. But I figured I should probably go educate myself a little better first. So they had also mentioned another talk, which was given by Halvar Flake at Infiltrate 2011. And by the way, I'm going to put these slides up as a PDF somewhere. It'll be either on the CackalackyCon site or somewhere findable. And all of these talks, both the videos and very often the slides in PDF form and possibly even a paper that underlies it, again, all available. So I've got all that in the slide notes, and anything that I say that sounds interesting, you can go and actually hear it from the people who did it by following those references. So I'm getting a little farther this time. I'm getting about every third word instead of completely not tracking. I didn't really understand the details, but the concepts are still fascinating. And so what I want to do is I want to take you down the rabbit hole with me on these concepts. Anything interesting in these next few slides are my attempt to summarize the basics of the science of insecurity talk. Anything interesting in those slides comes from Meredith and Sergey and Len. Anything that doesn't make sense is my translation layer, trust me. One thing that we have to sort of have as a baseline is what Turing complete means. So who in here is comfortable with the term Turing complete? Cool, less than half the room. I feel better because I didn't know what the hell it meant either. So a Turing machine, invented by Alan Turing, is a theoretical computer. And it's basically, there's a tape that symbols are printed on that represent computing instructions. And the tape can move forward and backward, and the machine can read the instructions and write the resulting output back onto the tape. So it's a pretty simple concept, but despite how simple this is, a Turing machine can simulate any computer algorithm. So a Turing complete system means a system in which a program can be written that will generate an answer when presented with a series of input. So if a system is Turing complete, it can be used to solve a computational problem. And Turing complete systems appear in places that you really wouldn't expect them. The thing that a Turing machine cannot do is it can't take another Turing machine and decide if that other machine will ever terminate. It's called the halting problem, and it's uncomputable. So trying to decide an undecidable problem actually turns out to be the root of a lot of insecurity. So this quote, "The illusion that your program is manipulating its data is powerful, but it's an illusion. The data is actually controlling your program." Everything in our world of programs and software and things that run on computers is distributed, it's composed. So programs consist of many components flying in hopefully tight formation. And these components have to do two things at a minimum. The first thing they have to do is accept input. And as a corollary, they should reject input that isn't valid. And then the second thing they have to do is when two programs communicate with each other, you want the interpretation of that communication to be the same on both sides. So if I say to Mike that the sky is blue, and he walks away thinking the sky is green and goes and looks for a tornado shelter, we have a problem. And the way that programs determine the meaning of a message is with a parser. And so you need to have parsers on both ends that interpret the input identically. This is the point where you can start to have problems, because if your parsers don't interpret those inputs identically, then you may end up with state on one side that is not what is intended from what was sent on the other side. Or if it's an attack, you may have state that is what's intended, but it's not what you intended when you wrote the program to receive the message. So input handling is one of the keys here. Is this input good? Is it valid? Or is it possibly harmful? And checking input to validate it can be an unsolvable problem. So again, this is where we get insecurity. So when you think about the concept that X runs on Y, some of the obvious ones are inputs execute on parsers. It's not just that the parser is processing the input is executing on the parser. Packets execute on TCP/IP stacks. malloc and free execute on heap managers. Binary format metadata executes on loaders and linkers. And then page tables and global descriptor tables and interrupt descriptor tables execute on an MMU. I hope you understand what all those words mean. I understand it a lot better than I did when I started, but again, this was kind of foreign to me. This means, or one of the fundamental principles here is that inputs are a language. They have a grammar. And understanding what the grammar is of that language helps you to interpret the language, helps you to first recognize it and then interpret it. So if we break this down, going back to the previous, IP packets are a language. They have nested structures. They have length fields, so they're weakly context sensitive. We'll get into that in a minute. And the stack, the IP stack, is a recognizer at every layer for every protocol. In servers, like SQL servers, valid requests make a language. In memory managers, heaps make a language. In function call flow, valid stacks make a language. And we get context sensitivity again here because which bytes are data and which bytes are metadata. So if you have more context than your program can handle, you start to be in trouble, because that means that the input you get may cause your program to do something you don't expect. One of the indications you get from that is that the simpler the input language is and the less context you need to handle the input language, the safer you are. So, how do we get there? Languages have hierarchy. This is language theory, Noam Chomsky, not just programming languages, but any kind of languages. So a regular language has no context dependency. It's very easy to work with. If you have two regular expressions, you can decide pretty easily whether they express the same language or not. Then you get a context-free language like Perl. So you have a grouping thing. Perl regular expressions can recurse on themselves. And that makes them a context-free grammar. Context-sensitive languages, we're moving up the complexity levels, they can refer to other parts of the tree. So if you have a payload and it has a length that was specified earlier in the packet, you have to refer back to that to make sure the length field specifies the same length as the payload you actually got. The failure mode here is padding attacks. And then recursively enumerable languages are the most complex types of languages, and just don't go there. So any sufficiently complex input is indistinguishable from bytecode. Again, from that talk. And magic. And the corollary is that any code that takes that input is indistinguishable from a virtual machine. So some languages are harder to recognize than others. If you have a regular expression, you have a finite state machine. So you can express simple nesting, but if you're trying to do something complicated, you may need more complexity. You may need to combine data. So if you try to parse a more complex language with a regular expression, you're going to get in trouble. You can't, with a regular expression, you can't easily parse recursive nested structures. So Internet Explorer 8 had a problem with a CSS module where they tried to build a protection tool, but it was actually not complex enough to handle the inputs that it was receiving, and so it created new vulnerabilities. And when you're performing validation, you have to make sure that you match up the strength of your validator with the strength of the input that it's getting. Regular with regular, context-free with context-free, etc. So what happens when input recognition fails? Internal code gets something that it doesn't expect. And primitives are exposed, so you can get things like memory corruption, implicit data flow, or unexpected control flow. So SQL injection is a recognizer failure. What escapes the escape symbol? Being able to slip in and unescape the escape symbol is a failure of the recognizer. And that is a language problem. That's what leads to SQL injection. In memory managers, heap metadata exploits abuse the context sensitivity. So heaps are complicated and they can be exploited if you can properly do metadata overrides. And I love this. This exploit technique is called heap feng shui. So Alexander Sodorov, that's who you research for that. So in each of these cases, the problem is that the piece of code looking into the data can't make a determination whether the next step is going to be correct in the context it's in. There's context beyond what the code can handle. Buffer overflows, overriding return pointers on the stack. This works because valid stacks are a language, and the language is so complicated that to unwind the stack frames, you really need a fully Turing-complete virtual machine. So this is what the dwarf standard offers, and this is where that 2011 talk comes in. We'll get to that. these failures result in the birth of a weird machine. And a weird machine is a term that was coined, I think, in 2009, possibly, but it's when you have a more powerful programmable execution environment than you think you do. So input into a program drives changes in state in the input handlers. And you have to be confident that those state changes are going to proceed in the way that you expect. The structure of a program is such that you have basic blocks that do recognition. These are things like the parser, the recognizer. And then some blocks are things you want to do, so processing components. When people write code, I am told, you don't really generally think about you're going to recognize everything first, and then you're going to parse it, and then you're going to hand it off to the execution that you want. Code ends up getting written piecemeal, and so you get a little bit of parsing here and a little bit of recognizing there, and then it does something, then you go back and parse the next bit, and then you recognize, and then you do something. Fragmentation attacks take advantage of that. And so when you don't do all the checks that need to be done, this is where you can have things like memory corruption. So an expectation in the code is not fulfilled, something unexpected happens, and you get a weird machine. So it's a more powerful computational structure, and it's driven by this crafted input. Make sense so far? Cool. Oops, that's the wrong direction. So this is the fundamental message from the Infiltrate 2011 talk. Exploitation is setting up, instantiating, and then executing a weird machine, programming a weird machine. Vaguely understood input languages are then the mother of zero-day. Because if you don't understand the input language, you can't really determine whether it's a valid message. And even if you understand the input language, combining the flow of input handling and input processing opens you up to these problems. So that's what Halvor Flake gets into. And you lose the ability to expect secure computation from whatever program you're running. Sergey Bratis has online a weird machine zoo. I love that. And he also has links to other collections like Accidentally Turing Complete. And by the way, the critter here, there's a deviant artist called A Mechanical Mind, and that's where I swiped this image from. So I want to give him credit and also say he has 1 million of these. They're made out of watch pieces, and they're beautiful. So this principle applies all the way up and down the OSI model. If we start at the bottom and we start at layer 1, Travis Goodspeed did a talk at Woot 2011, and it was on packet in packet for layer 1 injection exploits. So he called back to Orson Welles' War of the Worlds. How many of you are familiar with how War of the Worlds was introduced to the American public? Oh my God, history and people, I love it. So it was a radio broadcast, but it intentionally started after the station identification and the general announcements that you get that give you context. So he was able to convince his listeners that they were listening to legitimate news broadcasts of an alien invasion rather than tonight's entertainment on the radio. A packet-in-packet injection relies on the same principle. You miss the start of a frame, then what happens? So Zigbee has packets with fields in the header and then a body. And one of those header fields is a sink. So you have a preamble, then you have a sink, then you have the body. What happens if you put a sink in the body? Hardware doesn't know what to do about it. That's not my job, that's layer 2. So if a symbol error occurs in the preamble or the sink, the receiver can also think that the body is a new packet. You end up being able to embed a packet in a packet and do something unexpected. Encryption actually eliminates this problem because clearly you're making a clean differentiation between the header and the body. So if you can attack layer 1 in packet radio, where else can you do it? How about Ethernet? Same principle applies. It's a fairly esoteric technique. You have to have custom hardware to execute it, but the concept still holds. Moving up the stack. Layer 3. this is a great paper. This is the part where I start to understand it, thank you. But they showed that they can map between BGP and a logic circuit. They can create simple networks with routers that have basic BGP configurations that simulate logic gates, clocks, and flip-flops. And you can interconnect that to create circuits. So under reasonable assumptions on message timing, BGP can be Turing complete. And so they have a new method for studying the complexity of analyzing BGP configurations and exploiting this. They're also saying a few other things that I don't care about. But the idea here is we find Turing completeness in the most unexpected places. The really cool stuff is at layer 7. So this was a presentation at WOOT 2013. And the TLDR is that Rebecca Shapiro created a Turing machine in Linux from relocation data in an ELF file. So ELF is the executable and linking file format. And basically she hid code in the ELF metadata for ping and got a root shell. So this ELF format is basically everywhere. It's run whenever processes are set up and serviced or dynamically linked. And the loader can be tricked into performing computation by presenting it with well-formed but crafted ELF metadata. So that metadata and symbol table entries can act as instructions to cause the linker loader to perform arbitrary computation. And they actually had a proof of concept of constructing ELF metadata that implemented Turing-complete brainfuck language primitives. Also, anyone who names their language that gets points. And they were able to use that to insert a backdoor into an executable. The Dwarf Talk, 2011 at ShmooCon, what they did is Dwarf bytecode is exception handling. So all GCC compiled binaries have this, and it describes the stack frame layout, and it's interpreted to unwind the stack after an exception occurs. So a process image will include the interpreter for the Dwarf bytecode, and it can be written to have the interpreter perform almost any computation. So it can also be Turing complete. So Dwarf expressions are essentially functioning like assembly language. And the computation works like an RPN calculator. So you can backdoor a program such that the program works normally until an exception is thrown. And then you can return from that exception anywhere in the program with control over most of the registers. So this means you can modify no executable or normal program data, and you can still hijack the exceptions to get a shell. Very cool. Page Fault Liberation Army. Again, people with a sense of humor. Julian Bangert, he created a Turing machine in the x86 MMU by way of address translation. And he has a demo on GitHub. You can fly a glider around a screen. So trust analysis, basically determining whether a computer will not execute some classes of computation, generally assumes that computation is captured by an instruction trace. And what he showed is that computation is possible on x86 processors without executing any CPU instructions. So it's driven solely by the interrupt handling and memory translation tables. The processor gets trapped in a series of page faults and double faults without successfully dispatching any instructions. And the hardwired logic of handling those faults is used to perform the computation, as well as memory reads and writes. So they can even use this to perform branches and loops if the memory is set up and mapped perfectly. So it's a proof by construction that the Intel MMU's fault handling mechanism is Turing complete. And they constructed an assembler that translated move, branch if zero, and decrement instructions into C source, set up the processor control tables, and the CPU computes by attempting to fault without ever executing a single instruction. The one thing all of these have in common so far, other than being weird machines, is that they're all 6 to 8 years old. So these papers and talks were from 2011 to 2013. And I thought, surely it's 6, 8 years later, this is a solved problem by now, right? Nope. This is the 2018 RURSEC keynote, December of 2018, I might add. Same guy. Oh, by the way, Thomas Dillian is Halverflake, talking about the same thing he was talking about in 2011. So apparently this is still relevant. There are people looking at how to address these problems and suggesting how to deal with them. And that is the Language Theoretic Security crowd, or LangSec for short. And they have a wonderful single-page overview, which I have completely ripped off. So everything on the next 5 or 6 slides is from langsec.org/occupy. So the fundamental step 0 is full recognition before processing. Every piece of software that takes inputs contains a recognizer for accepting valid or expected inputs and rejecting invalid or malicious ones. And this code is often spread throughout the program and interspersed with the processing logic. They call that a shotgun parser by analogy to shotgun debugging. So this means you have a tendency to exploitation, and it makes programmers have false assumptions of data security. The way to solve that is do your recognizing, then do your processing. Another step here is to reduce the computing power needed to handle your inputs. If you're implementing a program that accepts SQL queries, and you know that you're only going to use a subset of the available SQL queries, then write your recognition, your validator, to only accept those queries. If you're never going to do an administrative delete or something like that, then that's not a valid input. You want to make sure that you use a protocol that's as low on the language hierarchy as possible. If you can use a regular protocol, a protocol that's regular, do it. If you can't, use something that's context-free. If you have to use something that's context-sensitive, make sure you understand the implications of that. So the other thing here is when you generate what you're going to send and receive, generate your parser out of the grammar for the language itself. So instead of writing it fairly loosely, take the grammar, generate the parser from there, and then validate your input based on that. With fixed length strings like an IP address, you could parse that with a regex. You really wouldn't want to. So you need to figure out where you are and use a validator that matches that level of complexity. So regular expressions have a finite state machine. Infinite recursion like XML or HTML requires a context-free language. Context-sensitive languages, you need a linear bounded parser. It's a Turing machine with a finite tape, so it's still decidable. The thing you want to avoid when you're validating your language is trying to compute an uncomputable problem. If you're trying to decide whether JavaScript is valid, the only way to really do that is to execute it or for someone to look at it by hand and figure out what it's going to do. You can't decide that with a validator. So protocols and file formats that are Turing-complete input languages are really dangerous. And this is where you lose security. If you can avoid using a context-sensitive or a recursively enumerable language, you should. And then the other thing is, try to make sure that the protocol you're using is going to be interpreted the same way on one side as on the other side. And this comes back to some work that Meredith and I think Len did, and maybe Dan Kaminsky in like the 2009-2010 timeframe around X509 and certificates. If you can request a certificate signed by a CA that is www.paypal.com nullbyte www.evil.com and get that signed, then when you present that certificate, is it going to be interpreted as www.evil.com or www.paypal.com? Different parsers may interpret it differently. So they went through and pulled a whole bunch of similar bugs out of X509 because of different interpretations as well as poorly scoped inputs. And they said they stopped when they got bored. They didn't stop because they ran out of bugs. So again, the other thing to bear in mind is that if you have ambiguous context-free grammars or context-sensitive and above, then you can't decide whether the two parsers are equivalent. You can't decide whether the message is going to be interpreted the same way. So Pastel's principle, at the birth of the internet, he said, be conservative in what you send, be liberal in what you accept. And this is how the internet came into being. This is why things can talk to each other today. But it's also why the internet works the way it does today. And they proposed a patch for Pastel's principle, which is be conservative in what you send, but be definite in what you accept. The goal here is to do secure software design and to avoid a lot of these issues. There's a really good overview that Meredith gave in 2013, what had been done and obviously looking into the future. And it's a tour of various projects that are implemented securely and different tools for language theoretic security. That's a great video as well. And the timeline that she builds goes, over probably 5 or 6 different years of projects ranging from web server implementations to simpler parsers that can be dropped into other coding projects. That group is on the langsec.org website, and they've been holding Langsec workshops at the IEEE Security and Privacy meetings, symposiums for 5 years? I can't count quickly, 6 years. These are a wealth of interesting information. The keynote by Dan Geer, so I'm a Dan Geer groupie. I will read anything Dan Geer writes on any subject. He has the wonderful habit of putting his keynotes and talks in clear text on his website. And about every 6 months, I go to his website and see what's new. That keynote is amazing. The DARPA keynote from 2018 is also fascinating. And this, in addition to the proceedings of the workshops, they also have links to all of these different talks and to a variety of tools that have been developed. So if you would like to learn more about weird machines and how to handle them, this is the way to do that. That's what I've got.